connected, the internet should not. So you cannot use your cell phone. Your cell phone should be turned off. And also you cannot use the memory function, the calculator. So please bring your simple calculator. So then it will be the 20 questions for the multiple choice. Each of them will be worthwhile 2 points. So it's pretty much generic. So first thing is that I'm going to make a question from the textbook. So you can study from your textbook, the exercise and the sample question, and your homework and your project will be helpful. So please prepare your midterm exam based on the class activity. Then for the open-ended question, it's 60%. That includes 50% of short answer. I'm going to ask several questions from your exercise lab. Okay, that probably include the Unix command and the Linux and the Unix, the command and the shell, the functions. So I'm going to ask very simple. If you already did the project as well as the exercise, so you can easily answer. Then the other 45% will be the open-ended questions. So I cannot give the all details, but you can imagine several questions from the scheduling. I'm going to provide some process state. Then you can calculate the number, the average waiting time, average response time, or turnaround time, and so on. And also you can expect some of the question from the synchronization. I'm not going to ask the exact source code, the program language. However, I may ask the pseudocode, which means if you understand the algorithm, you can fill out the blank or part of the algorithm to satisfy with the given condition. Okay, so I'm not going to ask the knowledge of your program language or the programming skill, but the knowledge of the algorithm. Okay, then another part is the process, the management. From the process management, you may expect several questions. So that will be pretty much 1 hour 15 minutes. So which means. So it can be pretty much generic question, not very difficult or comprehensive questions. So final exam may be the more specific, but the midterm exam we have only 1 hour 15 minutes. So first thing, please read the textbook. That is the first one. So because when I make the question, I usually look up the textbook, then make the question. So that is the first thing. You can do that. Then you can use the PPT file, but PPT file means some information details. So please rely on the textbook, then use your PPT file, and plus other class activity, including homework, project, and exercise lab, and so on. Any question regarding to the midterm exam? For the final grade, so usually it's 20 to 25%, but it depends on your overall performance throughout the semester. And also, do I apply curve? Yes, but my style is I'm going to first the undergraduate and graduate will get the different curve if needed. And for if I need to I need to apply the curve, I usually focus on the average score for the graduate student group around 70 or the higher than the 75 on average. So then if your average of the midterm score is around the 60 or 65, so I add up just the uniformly +5 or something like that. Okay, not considering the range of your the score. Okay. We do not have any questions, so we need to speed up to cover the chapter 5. So for your reminder, we are talking about the synchronization issues. So since we have the very limited research, also we are going to share some research like the thing about the shared memory or the file or the resource. So there might be race condition. Race condition happen when you have the shared resource. It doesn't have to be only the file or the variable. It can be any kind of resource. any shareable the resource. But when you have the multiple the consumer, which means the multiple process, there might be race condition. We cannot guarantee the output of the processing. So to synchronize along the multiple processes, so we need to think about the solution. That solution should satisfy with the 3 requirements. First one, definitely that will be the question of the midterm exam. How many students can use the toilet at the certain time? Only one. It's the mutual exclusion. So only one process can access the shared data. Then second, it's the progress. In other words, deadlock free. Okay? Only those who are waiting outside of the bathroom will participate in the voting. Who will be the next process? Okay? So deadlock, so to understand the progress, the deadlock free will be the easier the concept to understand the progress. It will not be stuck. Eventually we will decide the next process, next person to use the toilet bowl. The third one, such a waiting time should be bounded. Okay? If we need to wait forever, that's not fair. Like the starvation free. So deadlock free and the starvation free. So mutual exclusion, and second is the progress. Third one is the bounded waiting time. It's the 3 requirements for the solution. Some of the solution are satisfied with all of this perfect. But if we pursue all 3 requirements for the synchronization problem, sometimes the algorithm is going to be more complicated. But we pursue such a thing. So we talk about the algorithm 1 and algorithm 2 last time, which is very simple. Basically most of such a synchronization solution use the lock. So you can think about such a lock. What key to access that? But how to deal with such a key may be different solution. Okay. Also, we need to monitor who is waiting, who is enter, and who is leaving, something like that. So by considering such a thing, we talk about algorithm 1 and algorithm 2. Algorithm 1 uses the shared data. By the way, to address this problem, operating system provide the data structure. New data structure is a critical section. When we have the sequence of the instruction of the process, okay, whenever certain part of instruction programming code need to access the shared data, operating system realize that this may cause the problem. So before the process to use such a shared data, we write the operating system apply the entry section, certain code, and leaving when the process leaves such a shared data, it's an exit section. So operating system define critical section where process are accessing shared data. Before it's an entry section, after entry section. The others are just normal instruction, like the remainder section. So operating system use such a different the additional data structure to avoid such the problem. Okay, so for the simple algorithm one use the shared variable turn. We can semantically we can understand the turn is whose turn is that. Okay, and this one looks good, simple, but when you see the do while means it's from the beginning to end of the thread instruction, but such a critical section may happen several times. Okay, that's the reason in terms of critical section we can consider such an algorithm as a do while. Okay, it's nothing. It doesn't need the operating system add the do while loop for the user process. Instead, to understand such a critical section, it's not only one critical section. The multiple critical section will be happen for the one thread of the processes. So this solution using the shared variable turn it is good for the in terms of mutual exclusion, but as we discussed, the progress and bounded waiting time is bad. What if this one, is another process like the 10 or other, then nobody can use such a thing. And also algorithm to use the status of each process. Who is waiting for the critical section? Who are waiting outside of the bathroom? So using the flag. So 0 or 1, the flag 0 or 1. So false means no intention to enter the critical section. I'm not going to use the bathroom, something like that. So in terms of the process 1, because this is a two process case, so it's I, but you can think about the 1 and 2 for the I and J. So 1, this is entry section, so I'm intending to enter the critical section. Then if there's another process J, the process J will change the flag J as the true, like that. Then check whether the other process is using this one or not. If yes, so I should wait because it's a while of true, true, true until the other process changes the flag and then can enter the critical section. After you use the shared data from the critical section, you can change the flag, the undone. Okay? If the other process waiting like the same, the algorithm, then can enter critical section. In terms of mutual exclusion, it's good, but in this way, what if, for example, both of them are true? Whatever the reason, then we cannot address. Nobody can use such a critical section. So Patterson proposed the first solution of such a critical section problem. This is called the Patterson solution. So why don't we consider both algorithm 1 and 2? Algorithm 1, we can explicitly want to use the key turn. But the flag is the status. We can monitor the other. So why don't we consider both of them to address such a problem? So this is the solution. For example, this is from the process 0. Let's think about the two processes. So, or process I. So process 1 or process J. Okay. So we have two shared data. One is turn, another one is a flag. Flag 2. That means we have the flag 0 and the flag 1. Then apply the same entry section and the exit section for the process who want to enter the critical section. So this is the entry section for process 0. This is the exit section for the process 0. If we consider the process 1, the entry section will be like this. 1 is true, I'm entering. Then the turn is the 0. Wait, because I'm showing my intention, so you can get the key. If I enter, then you can get the key. So if you can give the next one, who can use after me, like that. So then this is the entry section of the process 0. Then similarly, the exit section is the flag I'm done and I'm done. So you can do that. Then let's think about the timeline. That will be easier. So we have two process. Okay. So process 0, process 1. Process 1, would like to enter the critical section first. So that means the exit section, this one will be executed. Flag 0 is true. So which means that I'm entering. I'd like to enter and give the turn to process 1 because I already exposed my intention. So give the key to the 1. Then the while check. This is the more important part. So flag when first, this is the end the operation, which means when can I exit the while loop? Either first or this one is a false, or both of them are false. In case both of them are true, we cannot exit the critical section. We cannot exit the while loop, which means we cannot enter the critical section. So for the process 0 to enter the critical section, this one true, false, or this one false, or both of them are false. So check the first time. Nobody used the critical section. So nobody used the critical section. Once you change the term value, this is a true and this is a false, because the process 1 is not started yet. That means flag 1 is a false. Okay, nobody used. And turn is 1. It doesn't matter because nobody used. I give the chance for the turn equal to 1. But it's not the other process is not used, which means nobody used critical section. So this is the false. False means out of loop. Okay, then process 1 can enter the critical section. So right now this one is in the critical section. Then process 1 is started and would like to access the critical section at this time. Then same thing, flag 1 is true, I'm entering, then because I'm entering, I give the chance to another process to enter the critical section. After that, then check the while loop. While loop of this process is the flag 0 is the 0. And the turn is equal to 0. So check this one. Flag 0 currently is the true because it's running in the critical section. Then turn is because I gave the toss key. Okay, so right now turn is 0. So which means this is true and true. So you need to keep checking. You cannot get out of the while loop. You cannot enter critical section until when? Until this process. There is a leaving flag 0
to false.
false. I'm leaving. Then this one is a false and this one is
False.
false.
So then critical section.
Even though this one is a method using the turn, we can actually address the problem of previous algorithm 1 and algorithm 2. So this is called the Pearson, the synchronization solution. Okay, let's check the 3 requirements. Definitely only one process can enter the critical section. Okay, only one, maximum one process. Then, what about the progress and the bounded waiting time? So, if for example process 1 is not in the not in the entry section, okay, which means process 0 should not be considered. How? Using the flag. Okay, even though both of them are false, so we can use the turn. Turn is false, then we can enter. The other process can enter critical section. Only the process who are in entry section can enter the critical section. Okay, so we can, by combining turn and the flag, we can address the problem of algorithm 1 and algorithm 2 that we discussed the last time. Okay, similarly, you can actually prove the 3 requirements by checking all the cases. Okay, by checking all the cases. So this will be eventually one process can enter the critical section because of the flag and the turn. And such a waiting time is after if not, then next while loop you can enter the critical section. So it's not the unlimited, the waiting time. This is a Pearson solution problem. It's only 2 process case. Okay, so only 2 process because right now the term is either 0 or 1 and the flag. How can we generalize for n number of process? We need to change this one for integer process number. And we can change the flag for each process.
Yep.
Then the problem is this one and this. Okay? We need to check if the other process, which one we need to check who is using the critical section, okay? Because whenever, how can we check the process who is entering? Flag, if flag is true, those process would like to enter the critical section. So we can select that process when a process is exit. How? So for example, we have the 6 number of processes, and then the 2 of them are the flag is true, which means they are in the entry section. How can we check? How can we select which algorithm is the simplest way? We can check the next one. Okay, whether flag is true or false. False, ignore. If true, first true will be selected. In the exit section, we can give the next process, I'm exit. So because I'm exit from here, it will be the out of the loop. Instead, why don't we check who will be the next flag is true? Okay, that process will be selected. Worst case, if no process are in the entry section, then false. Then going back to my process ID, then nobody will be selected because no process want to enter the critical section. Then in case there is any process who wanna enter the entry section, then we can select. That process will be selected because all the flag are false, so we can enter. So we will see such a solution in other such a algorithm in other solution soon today. So this is a Patterson solution. So there are a lot of variation of the Patterson solution. Okay, but those solutions are based on these two processes. The first, really old. Practically we don't use directly the Patterson solution because it's a two-process case. But we can generalize into the number of processes. If you take a look at the exercise, the exercise provides 2 or 3 examples of such n number of cases. Also today we will see one of the examples. Okay, so far we have talked about the software solution. We use just the algorithm like that. This is the algorithm for the entry section. This is the algorithm for the exit section. So operating system can involve whenever there is any interrupt or any sign to enter the critical section, then the operating system cannot add the module to the processes. Okay, it's a software solution. As I mentioned the last time, there are different types of the solution in the synchronization. One is a software, like this. Another one is operating system and hardware. The main problem of this one is what? It's expensive. Whenever process access the critical, enter the critical section, this algorithm should run, right? Another problem is this is a while keep checking. Okay, it should kind of spin lock. Then your system will be downgraded. So this is the easy to understand and implement, but practically not much used. But sometimes in the application program, you can directly implement like that to avoid any synchronization issues. So next solution, we'd like to consider hardware. In operating system, what is the hardware? Computer. especially CPU. So CPU provide a number of instructions. So such a number of instructions can operating system manipulate or change or define the new instruction? No way, it's a hardware level. So some of the CPU provide the specific instruction that can support the synchronization problem solution. So how can we do that? So as we discussed before, it's based on the kind of the locking. So how can we initiate the lock in terms of hardware using the interrupt? So before a process use the shared data, we can disable any interrupt. Without interrupt, the process cannot use such a hardware resource or shared resource. So then allowed to use the critical section shared data when exit the enable. So this is actually the basic idea of that, but we cannot directly use it because during such a critical section, we cannot, the other process will be stopped because we disable the interrupt. So to address the problem, the hardware, we can use the specific instruction to implement to address the problem of the critical section. Idea is we are going to use a lock, like the key, acquire the lock, release the lock. To do that, we define the couple. I'm going to introduce a couple of instructions that can be used for the synchronization. One is a test and set. This is a pseudocode to show how this instruction is working. Practically, test and set will be implemented by what? CPU. Okay? This is not the programming code. It's a pseudocode of the algorithm implemented in the hardware, your CPU. Like the increment or the add, move, like any other instruction. So this is an instruction. What's the difference? If you implement this one with the Java programming, any program language, test and set the instruction and test set the function, what are the difference? Output will be the same. The problem, difference thing is, if you implement this one as an instruction, this is atomic. Atomic means it cannot be recovered. You cannot split into them. So once this instruction test and set is started, should be done. Okay. However, in case of the programming level, there are a lot of I/O will be happen, so it can be interrupted in the middle. So that is the main difference. So we are going to use this test and set, the instruction, how it works. Can you understand the meaning of test and set from the pseudocode? We have the variable, like the input. Let's say the lock. So as it suggests, the lock is a false. So if we apply the test, so what will be the output of test and set of lock? Output. To understand, so input is the target, Boolean, the RV, return value is the target, it's the same thing. So RV is the same thing as the input. And target is always changed to the true. So input variable always changes the true, then return original value, which means if we are using the test and set, the instruction, regardless of the input, okay, regardless of the input, output of test and set is the same as original value. If it was a true, true. If it was a false, it's a false. Then log value itself is changed to the what? Always true. So in this case, log is a false, then output of test and set is false. But the log value will be changed as the true. However, if this one is a false, true, output is the same as this one true, then lock value will be the true. So always change as the true, but output of this one is just return the same value as the input. That is the test answer. So how can we use this one for the synchronization solution? So this is the entry section. This is the entry section. This is the exit section. So to enter the critical section, we need to check the lock. If lock is false, for example, lock is false, nobody use. Then output of test answer is false, right? So while loop is false, so you can enter critical section. Then what about the lock value is set? It is changed as true. In case if the other process would like to enter the critical section, then check the test and set lock. So current lock is true. Output will be true. So cannot enter the critical section. So until when? Until the current process is leaving. So for example, lock is false. So once lock is changed as the false, then this one enter the critical section. This is the same algorithm as what? The first one. Algorithm 1. However, performance, this one definitely much faster. However, this one has another critical problem. It's called the spin lock. The other process, when a process is using the critical section, it's in the critical section, but the other process is keep checking test and set. Huge number of the instruction will be used. So it's the overhead of your system. But this algorithm shows how we can use the instruction, the hardware level synchronization solution. Another the popular instruction that we can use for the synchronization solution is a swap. What is a swap? It's a switch, the value. Okay? So, for example, in case the pseudocode of swap is very generic, so you guys can understand this one. So Boolean A, Boolean B. So true is a true. But true false, then it's a false true. And false true and true false. So we can use the two variables. One is a key, and another one is a lock. Okay? So, for example, initial value is a false, the lock, and key, we can get the key. And the key is a variable owner. So, for example, so entry section of this solution using the swap operation is, the entry section is this. Key is equal to true, then the while loop is until this one. This is the while condition, and we need to check this. So for example, first time the one process would like to enter the critical section. So key is true, and while loop, the key is equal to true. So currently it is true. So we can swap the lock and the key. So if you swap the lock and key, the key is used first and lock is done. So true. Then at this time we need to going back to the while condition. Then check the key is false is equal to true. This condition is false, which means you can enter the critical section. So right now this process in the critical section. If we have another process, so currently key is false, then lock is true. key, we need to change it. The key is equal to true. So this is a true. And while loop, key is equal to true. And swap log and the key. So key is true, so swap log and key. So true and true. So even though you swap, both of them are true. So key is still true. So we need to keep checking the condition, then run the swap, and going on until when? When this current process is leaving, which means release the log first. Then log is changing the first, then the log is a false and key is a true. If you swap, the log is a true and key is a false. So key is a false, so you can enter the critical section by leaving the while loop. So this is the solution using the swap operation. Still, it has the same problem, right? So it has the problem of the bounded waiting time, and the progress will not be solved like the algorithm 1 and 2. Okay, so to address that problem, so we can consider the additional code for the entry section. This is the entry section, and this is the exit section. Okay, so first, we are going to manage the waiting. Waiting is the similar as a key. It's a flag. Okay, if you think about the Patterson solution and algorithm, it's for the number of the monitoring the number of processes who are entering the critical section. Waiting true means what? I mean entry section. So I'd like to use the shared data. Then key is equal to true. So just like the previous one, key is equal to true. So then, so we have the key, we have the waiting. So then the while loop is the waiting I and the key. So this is actually generalization of the previous solution. So check the key is equal to true. If the process is entering the critical section, so this is a true, and the waiting is also true. So this process I is waiting is true. Both of them are true. Okay, so we need to run the while block. Key is test and set of the log. So current log is a false. So if log is a false, key will be changed as the false. Okay, then this we need to going back to the while condition. So waiting is true, but because of the key, from here we got the key. So this is a false. Okay, log is moved to the key. So this is a false. Then can enter critical section. Currently, this is a true, and this is the current condition. So not much different from the other. But if we think about another process who is entering the critical section, using this one. So another process, let's say J, the waiting of J is the true, then the key is true, my intention, then the while, and waiting J and this is the key. So this is a true, this is a true, so we need to check the test and set log. Currently log is true. This process is using. So key still true. So it is keep checking. If you have another process, like the J plus 1 or the K or not any process, they are waiting. Okay? Then when This one is the exit. The exit, I will give the 1 minute to understand the meaning of this one. Currently, this is the I process. I, then the J is I plus 1, which means next process.
Yep.
And check this. Let me break down the while loop. The while. J is not I. What does it mean? J is not I. Because we are going to keep checking the next one, next one, next one. Okay? So if you have the 10 process, this one is a 0. 0, 1, 2, 3, 4, 5, 6, 8, 9. Then going back to 0. If until the next process is not the same as me. Okay? Only one round of checking. I'm going to check all the student only one time. Okay? If going back to me, that means I already checked. So that is the first condition. Then and so this one is not waiting of J. So what does it mean? If the next process is not checking, it's not waiting, so it's in the, let's say the process 0, 1, 2, 3, 4, 5. 5 process case. And the current process, this is a current process. Then leaving. Then the J will be 1.
Yep.
Plus 1. And check whether if this is a false, which means not waiting. The false means false and not of false, which means this one will be true. Okay? True, and this is not me. So if this is a true. True and true means what? I'm going to skip the next process. This one, we do not select. Okay? Then, this means the next one, the J is changed into 2. Let's say this is waiting. This one is J equal to 2. And the process ID is equal to 2. So it's waiting. In case of waiting, then this one is not, definitely it's not me. And the waiting, this is the true, not means it's a false. So true and false. This one is false. So you can out of this while loop. So while loop is this one. If J is equal to I, which means it's a false, false, false. Next, next, and going back to here. So if not, yes, it's not me. Then the lock, this is waiting, is a false. Waiting J. This one waiting to J is false. Then leaving. Then what if here? So going back to here, so check the waiting J. This is a changed by this process. So this is a false. False means this one, and even though this is the true, then out of the while loop can enter critical section. However, if J equal to I means all false, 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 then the 0 is 0. Then the lock is false. I can just change the lock. Then any process who is entering the critical section can get the lock. Okay? So exit section actually determine what? Next process.
Yeah.
From where?
From this.
From entry section. How does it know who are in the entry section? Using this algorithm. Who is true? Okay? Who is true? Who is waiting? Okay? Using this the condition, this process, the leaving process can select the next process from the entry section. That is the exactly same definition requirement of progress. So, is it the deadlock? If one process is waiting, then that process will be selected. Okay?
Yeah.
Then the next process. Maximum how many times? One round of the process. It will eventually get the critical section. So this is the perfect solution using what? The test and set. Test and set instruction. Once again, this is the entry section, this is the exit section. So entry section pretty much is similar as the previous one. So I'm not going to explain the details. But to enter the critical section, we need to get the lock. Okay, either lock is a force, then the lock is a force, then key is a force. Key will be changed at the force, then I can enter. Or using the weighting is changed by what? The other process currently in the CS critical section and leaving. If that changes the weighting, then I can enter the critical section. Either of that. So that the exit section is actually the kind of voting. Who will be the next process? How can we check? Next one, +1. So this is a modular. Okay? Because if we have the 5 process, the next one is a 0. If current process is 2, 3, 4, 0. Okay? 1, 2, if same, then just nobody wait. Then release the lock. Anybody who try to enter critical section can get the key. However, if there is any waiting, that is true, that will be force. Okay? Then force means out of the while loop, then give the key. Yeah, so weighting is a force, so because of weighting is a force, the next process will enter the critical section. Okay? In terms of the 3 requirements, it satisfies all 3 requirements of this one. Any problem of the solution? Still, you can see the while loop. It's a spin lock. Keep checking. Okay? That will be the overhead of the entire system. Okay, so we need to find, in terms of the 3 requirement of the synchronization problem, it's okay. However, in terms of performance, it's not. So to address that problem, we are going to use the data structure that is called the semaphore. If I look up the dictionary, so semaphore is kind of signal like this. I don't just search. But when did you hear about the semaphore? IPC. So you did the homework. I don't think is there anyone who used the semaphore for your mini assignment? Not many. One of the reason is semaphore usually used for signaling. Not communicate. It's communication, but if you are I would serve for what is that? The military in my hometown, my home country require 2 years of the military service compulsory. So my specialty was the driver, so it was okay to drive. But some of them is for the missile or the cannon or the rear, the arm and handling such a thing. At that time, they are using sometimes the flag to communicate. That is also used for the communication, but very limited. Like if you hold the 2 flag, or I think one of the good example is when the airplane, the touchdown and approach it to the airport. Somebody can use this one. They do not communicate through the microphone or whatever. It's really noisy. Okay, so to stop and keep going, they can use a flag. That can be used for the communication, but very simple communication signal like that. The semaphore can be used for the inter-process communication also, but it's not for the generic communication. Instead, it's just signaling like this. So we are going to see how we can use such a semaphore for such a signaling to address the problem of the synchronization. So semaphore is OS provide. So But we have talked about the software solution and the hardware solution. This is kind of operating system solution because OS provides such a data structure, semaphore. So semaphore, what is a semaphore, by the way? Semaphore is the just integer value, okay? List of value. That is a semaphore. Semaphore is just simple data structure that include inside the data structure. It has a list of the value. It's an integer value. Okay? So we can represent each value as a process. So we can consider. So semaphore keeps the list of a process. So we can think about imagine how we can use a semaphore. If there's any process who would like to enter the critical section, keep in the certain semaphore. List of process, living, and so on. So to do that, there are two operations in the semaphore. One is the wait, another one is the signal. Wait is the decrease the integer value. Okay? It's an integer, it's a decrease the integer value. On the other hand, signal is increase the integer value. Okay? So for example, the wait, so if you define the semaphore, the A, then the wait A is decrease the value, and the signal A increase the value. Then, if we simplify such an integer value of the A as the binary number, like the maximum number 1, minimum 0, 0 or 1. So the initial value is 1, the weight A will be A value will be 0. It's a log. And the signal A will be 1 again. It's an unlog. So we can use such a semaphore as a log. So that is the idea of the semaphore solution. So actually this one is called the binary semaphore is called the mutex law. Anyone who heard about the mutex law? When I use, is there anyone who ever used the Windows 95? Really, nobody?
I mean, I used the computer when I was
95, if you ever used the 95, which means you are a little bit older than the other. So I used a lot of Windows 95 from the release date, like the 1994, 5. So at the time, I received the 30, 40, the floppy disk. I'm not sure whether you guys ever used the floppy disk drive.
Yep.
Oh, really?
Yeah.
I still. So it's good. So same as age level as me. So I actually used that the 30, 40, the disk drive to insert the 95, and the 95. When you are using the 95, there are a lot of times something pop up from the operating system, something lock problem. It's a mutex lock. Actually, that mutex lock coming from the disk. Unless when sometimes the operating system cannot handle synchronization problem, just the pop up. I cannot handle this mutex lock problem. We will see why that happened a lot. So that what you guys need to do is Control C or kill the process or restart the system. So that is actually coming from the binary semaphore. So there are different types of the semaphore. The binary semaphore, which has only 0 or 1. The 1 is the default value. So we can the wait and the signal. Wait means getting the lock, decrease the value. And the signal is the operation of that semaphore is a release the lock. There's another one, the counting semaphore is a general semaphore. General semaphore usually is not much used than the binary semaphore, but the counting is any number, okay, any integer number that up to n. So we can use such a binary semaphore for the mutex lock, okay, because it's a 0 or 1. So this is the example of how to use a binary semaphore in our application program. Each operating system probably you search the semaphore, how can we implement the IPC, inter-process communication. At the time you can actually initiate the semaphore like this. It's a 0 or 1, maximum 1, minimum 0. It's a binary semaphore. And from the wait, semaphore wait. So before you use this this random function, whatever the name, they are defined here, that each function would like to access the shared data. In this example, that is actually thread. So we'd like to implement the thread. So in the thread can access the global variable. Global variable is a shared data in this, the application program. Okay, so that calls the same, the synchronization problem. So how can they address the synchronization problem? Using the semaphore. It's getting the lock. Semaphore wait means it's getting the lock and do the critical section. In this case, a 3 function. And when this process is done, then the release the lock using the semaphore post. Wait and post. Post is the same as the signal, the different name. So this is one thread. One thread. Then in your program, you can create many threads that can address the problem of the synchronization. So this is the one. Probably some of you guys did use this one without any knowledge of the synchronization. So probably you're the senior or the manager. Why don't you use the semaphore init or semaphore wait and semaphore post? It's kind of a lot to use, or the generic you can use. So that is actually from the synchronization solution. So this is the operating system level. Most of the operating systems provide such the semaphore data structure, so and as well as the library. Okay. So this is semaphore. The problem is, it's still the semaphore waits, the semaphore process keep checking. Okay. The other process who would like to enter the critical section keep checking using the while loop, whether it's a release. What happens if you knock on your bathroom door every time? The person will be crazy, right? Instead, what will be the solution? You can write down your name. If you want, enter the critical section. If you want to use something shared information, if you want to use the toilet paper, just leave your name and you can stay. Then when the operating system or the person who lived then called or text message to them, I'm not sure whether that works, but that is one way to avoid keep knocking. So to do that, we can actually extend the semaphore to avoid the spin lock. Like we can manage the number of processes by decreasing and signal increasing. So remove the process. We can manage the processor who'd like to wait. Okay. Who is waiting? Then if selected, remove from that. So that is the wait and the extended wait and signal to avoid it's a busy wait. Okay, keep knocking to avoid such a thing. Then we will see another high-level data structure to implement this one. It's called the monitoring if we have a time. But each program language provide a library. So still, it's not. The problem of the wait and signal for the semaphore is whenever we need to access the shared data, like this, we need to wait and signal. Okay, wait and signal. What is this case? Process 0, wait and S, wait, Q. And the process 1, Q and S. Currently, we have the wait. Let's see that this one as a time like this. Process 0, wait, which means the process 0 get the log of S. And process 1 get the log of Q. And wait the S to Q. But Q is held by the 1. And also S is held by the 0. What happened? Keep waiting. Okay? That may cause the deadlock issue. Okay? Sometimes. So we will discuss about more details. What is the deadlock in operating system? How can we address it? So let's just think about the deadlock. Another issue is a lot of time. So we need to wait the semaphore, the signal. If your program is simple, we can just put and this in between the critical section. However, if your program is sometimes the critical, wait again the Q and enter the critical section of this one and the signal like that. It will be really complicated in the real the application and the program. What if we forgot the signal? Nobody can use. Okay, that is the reason Windows 95 before they have a lot of such a mutex lock problem even in the operating system. So you need to always use the wait and the signal, just like the after you use your the toilet or you do not return the key, then nobody can use. It looks like the keep locking. So this the mutex lock the synchronization solution using the semaphore. It not totally, but depends on how application developer use this one. If the miss the signal, it will be the problem. So it has a lot of problem. So later, each program provide a very high level structure of the critical section that is called the monitor. So monitor actually is not the, it's kind of high level, the data structure. Idea is, why don't we keep just a list of a process, okay? Then assign, if available, assign certain resource to the process that is in the entry queue. Then the monitoring, whether this is done, then done, the release, then assign another process. By what? The high level data structure. So for example, Java provide that. So in the Java, have you ever used the explicitly semaphore wait and queue? Nobody used. The reason is that outside the class actually uses such the high level synchronization solution. Okay, this is called the monitor to avoid such the mistake and the abuse of the lock. Before that, we try to see the three examples of how we can use such a synchronization solution. As I suggested, as I mentioned before, whenever we have the computer science problem, we try to first model what is really the problem is this. Whether this solution is the existing one or not by modeling. So then there are well-known problems in computer science. One is a bounded buffer problem. This is a producer and consumer problem, as I introduced. Producer and consumer, client and server and so on. Another type of the problem is the readers and writers problem. Like when you are dealing with a file. So file can be accessed by the many processes. And also database use a lot of such the problem modeling. And this one is when you have the multiple number of the resource by the multiple number of processes. So we have the dining philosopher problem. So first two are easy to understand. You have used a lot before. So I'm going to very briefly introduce these two. And the dining philosopher problem is when you have the multiple resources with the multiple consumer. So bounded buffer, I don't have to explain again what is a bounded buffer problem. It's the producer and consumer problem. So critical section is the what? The buffer, read and the write, such a buffer. So before we need to manage the, we are going to use the mutex lock, the semaphore for here. Let's say the shared data is n size number of the n size the buffer. Okay, then we are going to define the semaphore mutex. This is a lock. Okay, this to use the such a shared data. Semaphore full, semaphore empty is used for size of the buffer. Buffer cannot exceed certain size of the buffer. The certain size that is managed by the full, the semaphore. And also, on the other hand, it cannot be less than 0. Okay, doesn't make sense. So to maintain the size, the empty, so we can create the empty. So using these two semaphore, we can manage whether this is a full or empty. Basically, this mutex lock will be used for the lock. So for example, the producer, when a processor would like to write something data to the buffer, we need to get the mutex lock. That is the lock to write, and the signal, the mutex lock to release the lock. And also you need to check the wait, the empty, whether this is the empty. In case a buffer is full, so empty the end. So you can check the end whether this is the full or not using the empty, and whether this is the release. The should be empty. I think there is something wrong. Producer one item. Signal. I think that this is a signal the empty.
But full means 0. So signal 0.
This is the signal 0.
Full means 0.
Alright, so this one is not used for the lock, okay? This one is used for to maintain whether full or the empty. So before you enter the critical section to use that, need to check whether it's a full or not, okay? Then the signal is a full, it will be the man is for the then it will be added like that, +1. Signal is a +1. So full, the semaphore will be +1 and this one. This one is checking and so on. For the consumer to use to read that and get the lock, mutex lock here, and release the lock here. Then the wait full is because it's a consume, read the data, and the wait the full, the reduce the full, and increase the empty. So that is the producer and consumer. The readers writers is slightly different. How many readers is possible? Many.
Yeah.
But how many writers?
One.
So one. Okay, that is the different from the producer and consumer problem. So then we can maintain the lock for to write the data, and the RW mutex lock is read and write lock, and the read count. Okay, we will see the writer. Writer is simple. To write, we need to get the read write lock. Okay, so this is a read write the mutex lock. To write something, you need to get the this lock. However, readers, we need to maintain, okay, number of the readers also. So to increase the when a process enter the critical section read the data, increase the reader count. So to increase the reader count, we need to apply also such the locking. So wait the mutex and the read count plus, and here you can release the read count. Where is it? Here signal wait and the signal here signal no. This is here. So this is I think that it's a bad indentation. Wait and the signal. This one is used for to update the read count. Okay. So to update the read count, the wait and the signal. And later, once you exit the process exit, we need to reduce the read count. To do that, we need to get the lock for that, the mutex lock and the mutex lock. To access this one, so we need to get the read write the mutex lock and the read write release the read write the mutex lock. Okay, so there are the three. The lock are used first to increase the read count. So you can get the lock over here and release the lock here. This is one, and this is to reduce the number of read count. To get the lock here and release the lock here. Okay, so then the overall to access the shared data, that is the getting the lock, the read write the mutex lock here. At this time, the process cannot write the data. So that this one wait that wait and the signal this read write the mutex lock will be released once this one is So 3 read the semaphore are used, wait and cue, wait and signal are used. Okay. So that is the readers, writers. The last one is the dining philosopher. 3 minutes. So let's think about the idea of this one is we have the multiple consumer and the multiple resources. So, for example, these guys would like to eat the rice, but what they can do is eating or nothing. However, to eat the rice, so unfortunately, each person has only one chopstick. So to eat the rice, the process need to get
Chopstick.
the next one, chopstick. So if I take the chopstick from the next one cannot get the rice, the resource, okay, consume. So which means, so we have 5 processes and the 5 resources. To do something, to eat a rice, we need to get the resource from the next one. So how can we manage that? Idea is one simple solution. Only one process can eat.
That's it.
Yeah. So stop. Then the interrupt. What lock? The global lock. One lock. If I get the lock, then I can eat. Then after I eat, release the lock, and next process can get it. It's a simple. Okay. We can use that. Okay. This is a lock, and get the lock, and release the lock. Very simple. The problem, actually, how many chopsticks we have? 5, which means at most 2 philosophers can eat the rice. But if you use the global lock, the only one the philosopher can eat. So its utilization is less than half. So to address that, so we need to check the next one. Okay. If the next one is available, then take the mine and the next one and eat. Okay. But problem is, what happened? At the same time, all 5 philosophers get their own chopstick. Then check the next one. You guys can keep waiting. It's a deadlock problem will be happen. So next solution 1 is checking the next the chopstick. If get the lock, otherwise if you cannot get the lock, waiting. So if all process get the chopstick, the wait for its own chopstick, it will be deadlock problem. Okay. So this is the common solution, but we cannot address the full problem. So to address that problem, we can use the monitor. So at that time, to maintain who is requesting, who is not, so we can use such a monitor. I'm not going to explain the details of this, more the programming level. Okay, so but if you are interested in such a solution of multiple process and multiple resource, so you guys can use the high level, the synchronization, the solution at the monitor and so on. I'm going to skip this part.
So the monitor is already
Monitor is what?
Is it going to be covered in the meeting?
Oh no, so it's not covered in the meeting. Okay, so I'm going to skip the example. I already introduced some of the example of the synchronization. Okay, so that's the end of chapter 5. So on Wednesday we do not have the class on Monday. Okay, so Monday is off due to the Fulbright. Then we will have the midterm exam. Please come. I know that it's 9:30. They're not easy, but I'm going to start the exam on time. Then it will be 75 minutes the exam. If you are late, you will lose the time for the midterm exam. So then it's paper based. I'm not going to allow to use any other material. Only the pencil and the eraser. And please bring the calculator. But calculator should not be connected or not functional the calculator. Okay, so simple calculator to add or the minus and so on. Yes. 1 to 6. Then I'm not going to ask any question regarding to the monitor, but the other I'm going to ask the question. Okay, any other questions? Enjoy your the midterm week, and hope to see on the Wednesday the next week.